All right, so today I'm going to do my very best to try to finish up this discussion of the Brock Mirman model, the optimal growth model with uncertainty, that is with productivity shocks in the production function. I love this thing. Pen. There we go. Okay. Proposition 1 that we talked about in the last class, or perhaps the one before, does not actually characterize the long-run behavior of the Brock Mirman model. It just essentially establishes the existence and uniqueness of the value function and sets up the conditions needed to acquire and it sets up the conditions needed to establish a unique policy function that achieves the maximum of the planner's problem. That policy function, if you'll recall, was given by this. KT plus 1 is pi of KT ZT, right? Pi is this continuous time invariant policy function, which shows how the planner optimally chooses KT plus 1 given the current state of the economy, K and Z. Okay. Now Z, we know, follows this first order Markov process, and it takes on a finite number of different values, capital N. Okay. And we know that the capital stock has to reside on a compact set between 0 and K hat, where K hat is the max of either initial capital or this highest sustainable level of capital in the model, K bar, which is defined as the fixed point that the economy converges to if consumption is always 0 and the technology or productivity shock is always the highest one possible. Okay. Now, I said this in the last class, but because the productivity term is stochastic in this model, the capital stock, nor consumption, nor output is going to converge to what you guys understand as a steady state in the long run, like we've been talking about all semester. Okay. Hopefully, however, the Brock Mirman model is consistent with our endogenous variables converging to something called a limiting invariant distribution, right? Meaning that in the long run, and regardless of what the initial value of capital is, that we should be able to characterize the distribution of the capital stock, meaning what is the support of that distribution? What are all the different possible values that the capital stock can take? And what are the probabilities associated with each of those possible values? Ideally, we want the model to converge to this limiting invariant distribution, which tells us the stochastic properties of the capital stock, since it indeed is a stochastic process, since it inherits the stochastic properties of the technology shock. And that distribution does not depend on what the initial state of the economy is. So I'll get to your question in just a second. So just like in the deterministic model, where the steady state is independent of the initial value of capital, right? You either have monotonic convergence up or down towards the steady state, depending on what the initial stock of capital is. What we want here is for this limiting invariant distribution to also be completely independent of what the initial state of the world is. So that given enough time, we can fully characterize the distribution function of what is now a random variable. Tavoy, go ahead.
Oh yeah, that was what I was going to get to. Like, all capital evolves over time. We're now treating it as a random variable.
It is a random variable.
Yeah,
that's right. That's exactly right. And that's what I mean by this unique invariant limiting distribution. Now, Tavoy, remember, the shocks take on these values Z1 through Zn. Imagine for a moment that these values get closer and closer together. And or we can take the case in which there's only two possible values. Z1 is 0.99 and Zn is 1.01. Then what do you think the limiting distribution of K is going to look like in the long run? It's going to bounce around the steady state of the deterministic model, where Z is just assumed to be 1 forever, right? And so that's kind of what we want to think about here. All right, so that essentially the goal for this class today is to prove proposition 3. All right, now let me state it and then we'll start sketching through the proof. Proposition 3 says that in a Brock Mirman model with stochastic productivity term Z that follows a first order Markov chain with discrete values in the set Z1 to Zn, the capital to labor ratio converges to an invariant limiting distribution. In other words, in a stochastic world, it has a steady state, right? And the average value of K is the same as this. So this is also kind of interesting. So the average value of KT, that is the expected value of K in the long run, can be equal to the limit as cap T goes to infinity of 1 over cap T times the sum of all the observed capital stocks. By the way, this makes the distribution of K ergodic in the long run, okay? Where the expected value is basically equal to the average of observed values over time. Okay. So there are 2 things that we want to do to prove proposition 3, 2 steps. All right. The first one is that we want to show after a finite number of periods that the capital to labor ratio is going to be contained in a compact set that is independent of the initial value of capital. Okay, in other words, we want to show the following, that KT is going to reside somewhere on the closed and bounded interval. I'm going to call it K min and K max, okay, for all T bigger than or equal to cap T, for some T less than infinity. Okay, now just to be clear here, K min, K max, closed and bounded is a subset, a compact subset of 0 to K hat. So this is the feasible space that the capital stock can reside on in the model. But what I'm telling you is that assuming the planner behaves optimally here, as enough time goes by, the capital stock in any period T bigger than cap T is going to live on this smaller closed and bounded set, okay? In other words, this is the support of the random variable K, and it is independent. What's the independent sign? Is that independent? Yeah, it's independent of the initial value of capital, or is this independent? I can't remember what the sign for independent is. In other words, it doesn't matter what the initial value of capital is, right? Over time, the support of the capital stock as a random variable is going to be this K min to K max. And we will characterize exactly what these 2 values are, by the way. Okay, that's step 1. The second step of this proof then is a little bit more complicated or abstract, but it involves trying to actually characterize the unconditional distribution of the capital stock, right? And in other words, what I'm going to try to do is I'm going to try to write down an equation that is consistent with being able to find the cumulative distribution function for K. That means the equation depends only on things that we actually know, right? The policy function, the stochastic properties of Z, etc. Can we actually derive a closed form equation that characterizes the unconditional distribution of the capital stock? The answer to that is yes, but we'll show that today. Okay, any questions then before we get started here on step 1? All right, what I want to do first is show that there exists some minimum capital to labor ratio. Let's call it K min, such that the economy will never fall, the capital stock will never fall below this level once the capital to labor ratio is at least as large as K min. Right, so it's for far enough time out in the future, eventually we're going to get to a point where the capital stock, regardless of the realization of the technology shock, is never going to fall below some K-min. Okay, let's define what K-min is first, and then prove that that will happen. Okay, I'm going to define K-min implicitly as the following: K-min is equal to the optimal value of capital, given that the previous period's capital stock is also K-min, and that the technology shock that occurs is the lowest value possible. Okay, so let's do the thought experiment. Let's imagine that the sequence of Z's that we receive is equal to Z1 forever. It's the worst possible state of technology, and we just get hit with that every single period. Then what do we know is going to happen in this model? If we get hit with the same crap technology shock every period, then this model becomes deterministic, and the capital stock will eventually converge to a steady state. That steady state in which Z is the lowest possible is given by this K-min. It's the fixed point of this problem. KT plus 1 is equal to pi of KT, whereas Z is equal to Z1 forever. Okay, so K-min is implicitly defined by this equation. Okay. Let's assume that KT is greater than or equal to K-min. Let's assume that KT is greater than or equal to K-min. Well, that means that KT plus 1 has to be equal to pi of KT ZT, right? Remember, we're talking about the optimal behavior of the capital stock in this model. So KT plus 1 is just pi of KT ZT. Well, we know that pi of KT ZT has to be bigger than or equal to pi of KT Z1. Why do we know that? Why is pi of ZT bigger than or equal to pi of Z1? Prop 2. The policy function is increasing in both the capital stock and the technology shock. That's what we did in the last class, okay? Well, that means that KT plus 1 has to be bigger than or equal to pi of K min Z1, right? If KT is bigger than K min, then this term has to be bigger than this term. Again, that's by prop 2. The policy function is strictly increasing in the capital stock. Well, what is pi of K min Z1 equal to? That's just equal to K min. Therefore, KT plus 1 is bigger than or equal to K min. So if initial capital is bigger than or equal to K min, then KT will be bigger than or equal to K min for all T bigger than or equal to 0. See how that works? So we assumed here that KT was bigger than K min, and we showed that next period's capital stock also has to be bigger than K min. So as long as initial capital is larger than that minimum value of capital that we've defined implicitly here, then we know that the capital stock will always be bigger than K min for all T. Now, of course, this does not yet rule out the possibility that KT is less than K min. What happens in that case? Well, we can show that in finite number of periods, the capital stock is going to rise to the point at which it gets to at least K min or bigger. And once that happens, then case A kicks back in. The capital stock will never fall back below K min. How can we show that? Notice that the growth rate of the capital stock, so KT plus 1 minus KT divided by KT, can be written as pi of KT ZT over KT minus 1. because KT plus 1 is just pi of KT ZT. Well, pi of KT ZT over KT minus 1 has to be greater than or equal to pi of KT Z1 over KT minus 1, again by prop 2. Pi is strictly increasing in Z. Well, this is equal to pi of KT Z1 over KT minus, let me do a substitution here for 1. Notice that 1 can be written as pi of K min Z1 divided by K min, right? Remember, we've defined K min implicitly as being equal to pi of K min comma Z1. So we can just replace the 1 with that. Now the question is, what's the sign of this term? Okay, here we need to do a little graphical argument, so bear with me. We are going to have to assume here that pi is pi of kz is strictly concave in K. But I think that's a fair assumption to make. Why? Think about it. Let me sketch the graph of what pi probably looks like. So here are my K's, and here are my K primes. That is the optimal value of next period's capital stock. Pi of K Z probably looks something like this. And by the way, this will be pi of K Z1, since that's the case I'm talking about. If the bad technology shock were to occur every period, we know that the economy would eventually converge to a steady state. That is pi of K min, right? Well, that steady state, of course, is going to occur where the 45-degree line slices through the policy function pi. So why does it make sense that we can assume that pi is strictly concave? Because we know in the deterministic model that the capital stock converges monotonically to the steady state regardless of the initial point. So that means the policy function must slice through the 45-degree line at a slope of less than 1. So this would be K min, and this would be pi of K min Z1. Right? And the slope would be equal to 1, right? The slope of this secant from here to here would be pi of K min over Z1 divided by K min, which is exactly equal to 1. Now the question is, how does that compare to pi of KZ1 over K? Well, if we're analyzing the case in which K is less than K min, then let's pick a KT over here. What is this point? This point would be pi of KT Z1. The slope of this secant then is going to be pi of KT Z1 divided by KT. So that means that pi of KT Z1 divided by KT, the slope of this secant, is bigger than the slope of this secant, which we know is equal to 1. So KT plus 1 minus KT over KT then is equal to the difference, I'm sorry, is greater than the difference between these two. Remember that was on the previous page. So KT, the growth rate of the capital stock, is greater than the difference between those two things, which we know has to be strictly bigger than 0. Therefore, KT plus 1 is going to be bigger than KT when KT is less than Kmin. You guys see what's happening here? If the capital stock is less than Kmin, then what we're saying is that the growth rate of the capital stock is positive. So with probability 1, since we're dealing with a random variable here, the capital stock is going to be rising regardless of what stochastic shock hits. And so that means eventually the capital stock is going to rise above this value Kmin, at which point the capital stock will never fall below Kmin because of case A that we cleared on the previous page. So it follows then, after a sufficient number of periods, the capital stock KT will never be less than Kmin for T sufficiently large. So KT will be greater than or equal to Kmin for all T bigger than or equal to cap T. And you'll notice that Kmin, by the way, fellas, is independent of the initial stock of capital, right? It doesn't matter what initial capital is. We can characterize Kmin independently of K0 or Z0. Okay, questions about that? Now, you might imagine what the next step is here. We want to do the same analysis for K max. So I'm going to be a little bit lazy here and try to just rewrite some of this stuff. You can fill in new on your own, but I'm just going to kind of erase, and because it's the same basic argument, except the inequality signs are different. Let's assume that there exists some K max, okay, where K max is implicitly defined as the value that the economy converges to if we are hit with the best possible technology shock every period, okay? So the highest level of technology is hitting every period. We know then that we're living in a deterministic world, right? There's no more uncertainty. And the capital stock will converge then to a steady state. Whatever that steady state value of capital is what we call K max, okay? All right, let's assume that KT is less than or equal to K max. That means KT plus 1 is equal to pi of KT ZT, which should be less than or equal to pi of KT Zn, right? And we know that by proposition 2. The higher the technology shock, the higher will be the optimal value of capital in the next period. Well, pi of KT Zn itself should be less than or equal to pi of K max Zn. Again, by proposition 2, if we're assuming that KT is less than K max, then pi of K max Zn is going to be bigger than or equal to pi of KT Zn, because pi is increasing in the capital stock. Well, what is pi of K max Zn equal to? Well, that's just K max. That's our definition of this highest optimal value of capital given the best realization of the shock forever. Therefore, KT plus 1 has to be less than or equal to K max. So if initial capital is less than or equal to what we've defined as K max, then KT will be less than or equal to K max for all T. So it's an identical argument from the first part, except we've just reversed it. We're now considering the highest possible value of capital. How do you think this last part's going to go? If we take an initial capital that happens to be bigger than K max, what direction do you think the capital stock is going to move? Down. And with probability 1, and once it reaches that K max ceiling, or floor, I guess in that case, it's going to fall below that and never go above K max after the point. So let's consider a KT that's actually bigger than K max. Well, the growth rate of the capital stock then can be written as pi of KT ZT over KT minus 1, just like before. And that is going to have to be less than or equal to pi of KT ZN over KT minus 1, which is the same as pi of K max Zn over K max. And again, all that's by proposition 2. As you increase the shock, you increase the value of pi, or the optimal value of next period's capital. As you reduce capital from KT to K max, since we're assuming KT is bigger than K max, you reduce the value of the optimal value of next period's capital. All right, what we want to show now then is that this growth rate of the capital stock has to be negative. Can we show that? Well, we should be able to by appealing to the same logic that we did over here. Again, if pi is strictly concave in the capital stock, this is pi of k Zn, then we know that if we get hit with the same highest technology shock every period, that eventually the economy will converge to this, what we understand as a steady state, which we've defined as K max. Now, we've analyzed a case here in which we've assumed that KT is bigger than K max. So let's take some KT over here, which we know is bigger than K max. Pi of KT Zn. Sorry for my poor sketch. But the slope of this secant would be pi of KT Zn over KT, and the slope of this secant is 1. That is pi of K max Zn over K max. So pi of KT Zn over KT minus pi of K max Zn over K max is going to be strictly less than 0. So KT plus 1 minus KT over KT is less than 0. Therefore, KT plus 1 is less than KT when KT is bigger than K max. And so with probability 1, then, the capital stock is going to fall if capital is bigger than K max, which means that at some point, the capital stock is going to fall below Kmax. And at that point, the capital stock will never rise above Kmax for reasons discussed earlier in part A of that part of the proof. Therefore, KT must be less than or equal to Kmax for all T bigger than or equal to T. See what we've done here? We've basically proved then that KT has to fall somewhere between Kmin and Kmax for all T bigger than or equal to cap T less than infinity. And that this particular support of the random variable K is independent of initial capital and initial technology. So just like the steady state in the optimal growth model is independent of the initial wealth of the economy, the limiting invariant distribution in the Brock Mirman model has a support, a domain, if you will, that is independent of the initial wealth of the economy, right? For T sufficiently large, we know that the capital stock is going to live somewhere on this particular interval. And as Z1 gets closer to Zn, right, 0.99 and 1.01, Kmin and Kmax get closer to one another and just converge to the old steady state that we knew and loved in the deterministic model, right? That's kind of the analog of what's going on in the stochastic world, is that instead of a steady state, eventually we're converging to a point where the variables take on an invariant limiting distribution. They sort of bounce around in an ergodic way around what we used to understand as the deterministic steady state. Does that make sense?
Listen,
Yes.
what if we change the assumption and the random variable Z? What if we think of it having different shocks over time, not just the smallest shock or the highest shock?
It doesn't matter how wide Z is. The domain of Z, I mean, Z1 to Zn could be large, not so large that the capital stock takes on infeasible values, right? You can't have negative values of capital, for example. But this argument does not assume anything about the smallness of the set Z. Yeah. Other questions? Okay, let's go to step 2 of this proof, which is a little bit more, I guess, theoretically abstract, but is important to do. What we want to try to accomplish here is to be able to characterize this limited invariant distribution of the capital stock, or more precisely, the capital to labor ratio. We've just assumed that there's no population growth here, okay? All right, to accomplish this, let me define some notation that we're going to have to use. I'm going to define, now this is not production, but capital F of K given Z. This is going to be the conditional probability that the capital stock equals some value K in the current period, conditional on a particular value of Z in the current period. In other words, it's the probability, let's be clear about this, that KT is equal to value K, conditional on ZT being equal to value Z. What I want to do is characterize the cumulative distribution function for the capital stock, and I'm going to call that capital G. In other words, I'm sorry, not the cumulative distribution, the unconditional probability distribution. That would give you the probability that KT is just equal to some K, irrespective of what the current realization of the shock is. This is the thing that I want to be able to try to characterize. Now, I keep saying that word. What do I mean by that? I want to write down an equation that I can use that at least implicitly characterizes what G is in terms of things that I know. Like the Bellman equation implicitly defines or characterizes the value function, right? We've got the value function on the left-hand side, the value function on the right-hand side. The other things that are in the Bellman equation, we know what they are. It's the utility function, it's the parameter values, etc. Right? Can I write an equation down that actually characterizes the distribution, the unconditional probability distribution of the capital stock here in terms of things that I know? What are the things that I know? The optimal policy function chosen by the planner, pi, and the probability distribution of the stochastic shocks summarized by what? The transition matrix Q. Okay. I'm going to do this in a few steps here. So part one of step two, what I want to do is I want to be able to characterize f of k zj for any j between 1 and n. Can I write down what this particular conditional probability is for any possible value of z in period t? Okay, to answer this, let me think. What are the possible paths for reaching kzj in date t? How do we get there? What are the possible paths for reaching a capital stock of K and a technology shock of ZJ in period T? Well, let's suppose for a moment, I'm going to sort of work backwards here, by the way. All right, so try not to get confused here. Let's suppose that ZT minus 1 was equal to ZI. All right, so last period's technology shock was ZI. Then that means that the optimal value of capital in period T can be written as pi of KT minus 1, comma, ZI, right? Where ZI is the value of Z at date T minus 1. Well, if you imagine inverting this optimal policy function, then, assuming we know what pi is, we could more or less solve for KT minus 1 as a function, as the inverse function, let's say, of KT and ZI. All right, so in order to get to KT ZJ in period T, starting from ZI in period T minus 1, then KT minus 1 must equal whatever this is, okay? And that must be true for all I between 0 and n. Okay, now, given that information, let me ask, what is the probability then that ZT minus 1 is actually equal to ZI and that KT minus 1 equals this particular value that will generate the correct value of K in period T? That is, what is the probability that KT minus 1 is equal to pi inverse KZI and that ZT minus 1 is equal to ZI. Now, just to be clear here, I want to be, I already messed up a little bit of my notation. I want to know how to get to KT is equal to K and ZT is equal to ZJ at date T, okay? And so if we suppose that ZT minus 1 is ZI, then that means KT is equal to pi of KT minus 1 ZI. So in order to get to KZJ in period T, that means KT minus 1 is the inverse function of KZI, starting from some known ZI for any particular ZI. So what is the probability that we've got that right value of KT minus 1 and also that ZT minus 1 is equal to ZI? Well, we can write that down if we apply the law of conditional probabilities. That's just the probability then that kt minus 1 is equal to the inverse function of kzi, conditional on zt minus 1 being equal to zi, times the unconditional probability that zt minus 1 is equal to zi, right? I believe that's the law of conditional expectations. The probability of the joint event is the probability of the conditional event times the unconditional probability. Okay, well, remember how I define this. Guys, remember, this is the notation that I've adopted. This conditional probability I've called f of k zj. So this can be written as f of, let's see, pi inverse k zi, conditional on zi, times, I'm just going to call this p sub I. That's the unconditional probability that zt minus 1 is equal to zi. Now, we know what this is. We can get that from the transition matrix, Q, right? Remember what the transition matrix shows us. It's the conditional probability distribution of the z's for every possible state, right? We can do certain manipulations on the transition matrix. I'm not going to get into it, but if you subtract the transition matrix from the identity matrix and then invert that, it tells you what the unconditional probability then that z is any of the possible z's in any given period. I'm just going to call that pi. It's a function of the q's, is what I'll tell you, and it's known. It's derived directly from the transition matrix. Okay, this is the thing that we're after here. This conditional probability that we're going to use to help determine what G is. Okay. Let me then next ask, what is the unconditional? So here I asked, what is the joint probability that zt minus 1 is zi, and that kt minus 1 is equal to the value that would give me kzj in period t? Let me ask the next question. What is the unconditional probability that the economy reaches kzj in period t, starting with zt minus 1 is equal to zi? In other words, the probability that kt minus 1 is equal to pi inverse kzi, and that zt minus 1 is equal to zi, times the probability that zt is equal to zj conditional on zt minus 1 equaling zi, right? Think about that. So this is the joint probability that I described above times the probability that we transition from state I to state j then. So that's going to tell us then what the unconditional probability is going to be that the economy actually reaches kzj at date t. And of course, we know what this is. What is the probability that zt is equal to zj given that zt minus 1 is zi? That's just the transition probability, qij, and the rest of it is what we just characterized above. That's f of pi inverse kzi given zi times pi. Now it is straightforward to calculate the exact probability then of reaching kt is equal to k and zt is equal to zj, irrespective of what zt minus 1 is. Okay, this line here shows the probability that kt is equal to k and zt is equal to zj, given that zt minus 1 was ZI. Now what I want to ask is, what is the exact probability of simply reaching KZJ in period T, irrespective of what Z was in the last period? So that is, what's the probability then that KT is equal to K conditional on ZT being equal to ZJ? Well, to find that, you simply sum over all possible values of I, what we just found in the last step. Qij, f of pi inverse K Zj, I'm sorry, Zi, given Zi times Pi. If we sum up that conditional probability over all possible initial Z's, that is Zt minus 1s from I is equal to 1 to n, that tells us what the exact conditional probability is of Kt being equal to K, given that the current Z is going to end up being Zj. Now, what is the left-hand side of this equation equal to? Well, that's f of K given Zj, as I defined up at the top, right? So what do you see here? What is this? This is nice. This is a single equation that implicitly defines the conditional distribution of the Ks in terms of only things that we know, right? On the left-hand side of this equation, we have capital F. On the right-hand side, we have a bunch of capital F terms, capital N of them, right? And attached to those terms are these transition probabilities and unconditional probabilities of the Z's. The arguments inside of the F, we also know, because they depend just on the policy function. So this is an equation then that characterizes the solution, if you will, to F. Once we have that, it's easy to get G, right? I guess that's the second part of this. K is distributed according to some function G in the following. If we want to know what the unconditional probability that Kt is equal to K, we simply sum this expression over all possible J's and multiply them each by the unconditional probability that of Z is equal to Zj, right? So that would be the sum then from J is equal to 1 to cap N of Pj, that's the unconditional probability of Z being equal to Zj, times f of K given Zj. So once we have capital F, it's easy to calculate capital G. And again, you'll notice that the distribution of K is independent of the initial value of the capital stock, right? We now have two things. We know that given sufficient enough time, the capital stock must reside between K-min and K-max. And we also have enough information now to actually determine the probability that K is equal to any particular value in that interval, right? That probability is given by G. It's the probability that KT is just equal to some K, right? So for example, if I wanted to calculate the expected value of K in the long run, it can be, what is it going to be equal to? It's the integral from K-min to K-max of what? Of K times G of K dk, right? G is the probability density function, if you will, of the random variable K. Or alternatively, you can think of the integral from K-min to K-max of G of K dk is equal to 1. You sum over all of the probabilities, they should equal 1. You see how we did that? So I know it's a complicated concept, but G is known as soon as we know what F is. And F can be determined based on things we know about the model, right? It's the limiting invariant distribution of the capital stock. Okay, any questions about that? There is one final thing that I want to do before we leave today. Should have enough time to do it. I apologize because I've skipped around some. So in my notes, the next thing I did was solve for the policy function and the value function of the canonical Brock Mirman model, which we did, I believe, in the last class, correct? So let me now skip to, I guess it's section 1.6. And that is verifying the transversality condition. Okay. We know that the optimal policy function in the Brock Mirman model is given by pi of kt zt. And that this policy function must satisfy the Euler equation, which was u prime of ct is equal to beta expected value u prime of ct plus 1 times the marginal product of capital in period t plus 1 plus 1 minus delta. And it must also satisfy the period by period solvency condition. Ct is equal to f of kt zt plus 1 minus delta kt minus pi of kt zt, in other words, kt plus 1. However, what we haven't done yet is we haven't verified that the policy function that comes out of the Brock Mirman model, which is uniquely defined as long as all of those assumptions and theorems are satisfied, which they are, but we need to verify ex post that in fact the policy function indeed satisfies the transversality condition. That's the other key condition, right? When you guys are applying the dynamic programming theorems to a stochastic problem, what do? You set up you take the sequence problem, you write the Bellman equation, you use the Bellman equation to derive the stochastic Euler equations from the first order condition of the Bellman equation along with the envelope condition. You guys all know how to do that. But the other condition that must be satisfied by some candidate policy function, of course, is the transversality condition. That must be satisfied. The limit as t goes to infinity of the expected value conditional on date 0 information of the discounted marginal utility value of the state is equal to 0. Remember, the transversality condition is extremely important. Why? Because it guarantees that the household's lifetime budget constraint is going to bind. It's the essential condition that will guarantee saddle path stability in these class of models, even in a model that has a stochastic component to it. Okay, so we want to try to verify that indeed this equation is satisfied. Now, fortunately, this should not be too difficult, because why? We know that the capital stock for t sufficiently large is going to live on this set k-min to k-max, right? So the capital stock can never go above k-max, never go below k-min for t sufficiently large. Does that understanding then help us bound what is in the limited expression here? If we can prove that this term here is finite for any possible sequence of k's, we can pull it out of the limiting expression and the whole thing is going to go to 0, right? So I guess there are 3 parts to the transversality condition I want to look at. I'll call this 1, 2, and 3. KT, this marginal product of capital term, and then the marginal utility of consumption term. Well, let's look at 1. We know that KT is less than or equal to K max which of course is finite, for all t bigger than or equal to cap t. Okay, so 1 is certainly bounded for t sufficiently large. What about 2? Well, f of k evaluated at kt zt plus 1 minus delta is going to be less than or equal to f sub k of k min zt plus 1 minus delta. Why do I know it's bounded above by f sub k k min? Because the production function is strictly concave. So the lower k gets, the higher the marginal product of capital. So the marginal product of capital evaluated at kt is less than the MPK evaluated at k min, right? Because the second derivative of f is negative. Well, I'm going to argue that that's less than or equal to the derivative of f with respect to k evaluated at k min and zn plus 1 minus delta. Now here, I guess I'm going to have to make an assumption. And this would be that f sub k is increasing in z. I haven't technically made that assumption yet, right? That we know that f is increasing in z, but is the marginal product of capital increasing in z? Well, think about a Cobb-Douglas production function where z just hits the term linearly as, you know, zt times kt to the alpha. The marginal product of capital is alpha z k to the alpha minus 1. So the higher z gets, the higher the marginal product of capital gets. So the class of Cobb-Douglas production functions satisfies that. And I think that's an appealing assumption to make. The marginal productivity of capital should increase as the state of technology increases, right? Well, we know that this is some finite term, right? So that means this marginal productivity term is also bounded above by something. It's bounded above by this expression. And kt is bounded above by k max. The harder thing to show is that the marginal utility of consumption is bounded. But can I do that? Okay, the optimal value of consumption, I'm going to express that as some policy function pi superscript c as a function of kt and zt. What is it equal to? It is equal to f of kt zt plus 1 minus delta kt minus kt plus 1, which is pi of kt zt. Okay, so the optimal choice for consumption is equal to output plus 1 minus delta capital minus the policy function for kt plus 1. Okay, I need to know whether or not the slope, I need to know, first of all, how optimal consumption is related to current capital. In other words, if I raise kt, am I necessarily going to increase ct? I think the answer to that is yes, but let's demonstrate that. In other words, what is the derivative of the optimal value of consumption with respect to the state kt? Well, that's going to be equal to the marginal product of capital plus 1 minus delta minus pi of k, kt zt. Okay, let's see. This is a positive. This is a positive, but pi sub k is also positive, right? We know that the policy function for capital is increasing. The question is whether or not it's bigger than or less than f sub k plus 1 minus delta. Okay, here I'm going to have to recall a result that we got, I think, in the last class or maybe the one before. And that was, do you guys remember this? So we actually, in proving that pi is increasing in k, we found that pi sub k was equal to u double prime of c, and I'm just going to call this c star to indicate that it's the optimal value of c, times f sub k plus 1 minus delta divided by u double prime of c star, the optimal value of c, plus beta times the expected value of the second derivative of the value function evaluated at pi of k z comma z prime conditional on z. You guys remember this result? In trying to solve for the sine of pi sub k, we took the derivative of the first order condition with respect to k, and we solved it, and we got this. Now, what was the sign of this thing? This is easy to do, right? U double prime is negative. The marginal product of capital is positive. So that's a negative divided by a negative plus a negative makes the whole thing strictly greater than 0, right? Because v is strictly concave. So the second derivative of v is negative. But do you guys see, look at this here. What do we know about the size of this term that I just put a circle around? U double prime divided by U double prime plus beta expected V double prime. That's going to be less than 1, correct? That's a negative over a negative plus, the negative over the same thing plus another negative. So that's less than 1. So what does that mean about the relationship between pi sub k and this marginal product of capital term? So this thing here is less than 1. So that implies then that pi sub k of kz is strictly less than f sub k kz plus 1 minus delta, right? How cool is that? Now we can use that to figure out the sign of that, which has to be what? Positive. You guys see that? So optimal consumption is increasing in the existing stock of capital. Now, why the hell does that help us? Okay, what that means then is that CT must be greater than or equal to pi c k min zt, which is equal to what? F of k min zt plus 1 minus delta k min minus pi of k min zt. If consumption is increasing in the capital stock, then that means consumption must be bigger than or equal to the optimal value of consumption for the lowest value of capital for all t bigger than or equal to cap t. Again, because pi c is increasing in k. Well, that implies then that CT must be bigger than or equal to, let's see, F of K min Z1 plus 1 minus delta K min minus pi of K min Z1. So all I'm doing here is this equation, the second to the bottom must be true for any value of z, right? So, and also for the lowest possible value of z. So that means for t sufficiently large, that consumption must be bigger than f of k-min z1 plus 1 minus delta k-min minus pi of k-min z1. Well, what is pi of k-min z1 equal to? That's just equal to k-min. So this cancels with this, right? Which means that CT must be bigger than or equal to f of k-min z1 minus delta k-min for all t bigger than or equal to cap t, right? So as long as time is sufficiently large, we know that consumption is bounded below by some finite value. Why is that helpful? Because if consumption is bounded below, if it has some lower bound for t sufficiently large, and the utility function is strictly concave, then that means the marginal utility of consumption is bounded above by u prime of f of k-min z1 minus delta k-min. Right? The utility function is continuous on a compact domain. So if we can prove that consumption is bounded below by some positive level, it must be bound, the marginal utility of consumption must be bounded above by some particular level. Therefore, 0 has to be less than the limit as t goes to infinity of the expected value of beta to the t u prime of ct times f sub k of kt zt plus 1 minus delta times kt. U prime is positive, the marginal product capital is positive, k is always positive, so this expression here we know is bigger than or equal to 0. But we also know that it's strictly less than or equal to the limit as t approaches infinity of the expected value of beta to the t times the upper bounds on all three of these parts that we just found. That is u prime of f of k-min z1 minus delta k-min times f sub k of k-min zn plus 1 minus delta times k max. But you can see here that all of these things are finite. We can pull them out of the limited expression. They're not random variables, so we don't have to evaluate their expected value. And what are we left with? Some constant times the limit as t goes to infinity of beta to the t. Well, what's that equal to? That's equal to 0. So this limit expression is greater than or equal to 0, but less than or equal to 0. So it must be equal to 0, and therefore the transversality condition is satisfied. Questions? All is good in the world now. We have only one more task, and that is to study labor search models of unemployment, which are very interesting models. I look forward to it. What's this? You guys have any last questions about this then? You good?